Okay. So any question before we continue? So to summarize, okay, you have, if you apply Bernoulli equation for a compressible flow, this is your general relation. Integral of dp over rho plus v square over 2 plus gz equal to constant. Just you have to know what is rho function of p to proceed. And in case you have incompressible flow, then your equation is of the following form. Someone was asking me what this term is related to which energy form. This is called flow energy because it's related to the energy of the flow. So as the pressure is varying, the flow energy is varying. Okay, and this is related to kinetic energy, and this is related to potential energy. Okay. So, as we said, the Bernoulli equation is similar to a conservation of mechanical energy principle. And just as we said, we have, in addition to kinetic and potential energy, which we are familiar with, we have in addition the flow energy. Okay, and this means that I don't have any dissipation of mechanical energy because I don't have friction, or since I am considering regions that are far from boundary layers and far from wake regions. So in case I cannot neglect friction effect, I cannot use this Bernoulli equation. Okay, I should do something else, and we'll see in future chapters what will happen in case I want to consider friction forces. Okay. Now, concerning the following term, okay. So for Bernoulli equation, you can write it in several ways. You can write it in this way, okay, or you can multiply all your terms by rho. If you multiply all your terms by rho, all your terms will have the same unit of P, which is Newton per meter square. Okay, Newton per meter square. So always pay attention that all of these terms should have same units. So if I divide by, if I multiply by rho, I should multiply all terms. Here in this, when you put P over rho plus V square over 2 plus GZ, all terms will have as units meter square per second square. Okay. And finally, here, another way to write Bernoulli equation is to have all of terms of unit of length. If you divide, because if you divide these terms here by gamma, okay, so you will get P over gamma plus V square over 2G plus Z. P over gamma is called the pressure head. You know that from previous analysis of statics of fluids, we know that the pressure, let's say, is equal to P0 plus gamma times a certain height. So pressure is has the same dimension of gamma times height. So when you divide by gamma, okay, you will obtain the height h. This is why we say that this term has a unit of length, and it's called pressure head. So this is called the pressure head. This is called the velocity head, and also it will have a unit of meter. And this is for Z, okay, this is the elevation head. So you are free to use any of these three. Of course, you will get at the end the same result. But this is widely used. Heads are widely used when we deal with fluids. So if they give you the pressure head of a fluid, you can just multiply by gamma to get the pressure of your fluid. Okay. Now, let us do some analysis about pressure terms, okay? This term is called just the static pressure of the fluid. And this is, if you want, this is the pressure that will be measured by a certain manometer, okay, irrespective of motion. يعني whatever is the motion of my particle, I can measure whatever is its velocity, I can measure its static pressure. So it will not incorporate any dynamic effect, and it will represent the actual pressure of the fluid. Okay. Now, for rho v square over 2, this is called the dynamic pressure. And it represents the pressure rise when the fluid in motion is brought to a isentropic stop. What do we mean by this? Look, imagine that you have a certain flow with a certain velocity. If you force it to stop without having losses, its pressure will increase. Okay, and the increase in its pressure will be equal to this term. Why? Because since we are dealing with P plus rho v square over 2 plus rho gz equals to a constant. In case you are moving, your fluid is moving horizontally, z is not changing. Okay, if you force it to go from a velocity v to a velocity z of 0, then your final state will be as follow: P at state P final plus 0. So you can say that P final is larger than P by this amount. Okay, so the increase in pressure delta P is equal to the dynamic pressure rho v square over 2. So we define the dynamic pressure as the pressure rise when the fluid is in motion is brought to a stop isentropically. Isentropically means without losses. Okay, so I can still apply the Bernoulli equation. Now, for rho gz is the hydrostatic pressure. Okay, and it's not a pressure in a real sense, since it depends on the reference level selected. This means that if you change reference for z, the value of this pressure will change, but delta of P hydrostatic will be the same. Okay, so your selection of reference will not affect your result, because what you care for is delta z and not the numerical value of z. So we can say that the total pressure, okay, the total pressure can be measured as the summation of static, dynamic, and hydrostatic pressures. And therefore, we can say that for the Bernoulli equation, this equation states that the total pressure along a streamline will remain constant. Okay. Now, let us define what is a stagnation point and a stagnation pressure. If you have the following flow over a ball, okay, you have that for one of the streamline, you have a point that is characterized by a zero velocity. So here, for this flow, you have the following streamline. When it will be in contact with your ball, will, due to non-slip condition, will be forced to come to a velocity of 0. Okay, this means that at this level, since v is equal to 0, okay, you can say that you can calculate this is the maximum possible pressure along this line. You know why? Because as you move along this line, since energy is conserved, as you move, your velocity is decreasing and your pressure will increase. And this point is called stagnation point, and the pressure at it is called stagnation pressure. So it can be shown that there is a stagnation point on any stationary body that is placed into a fluid flowing flow. Why? Because whenever you have fluid motion around a body, at a certain point, when you have contact between the fluid and the body, you will have a velocity of 0 at this point. While away from this point, as you can see here, you will have separation. So you'll have one streamline that will stop at this level, and here in this example you have symmetrical streamlines that will deviate from the stagnation streamline, and you will have formation of the following streamline. So you can draw series of lines, of streamlines, and as we have seen before, beyond your object, you will have what is called a certain wake region. So here you will have formation of a certain wake region because of the separation of flow. Okay. So some of the fluid will flow over and some under this object. The dividing line or surface for two-dimensional flows is termed as the stagnation streamline, and it will terminate at the stagnation point, which will be characterized by a velocity of 0. So for symmetrical objects, as the baseball in the figure, the stagnation point is clearly here at the tip of the object. Okay. Now, how we can calculate the value of the stagnation pressure? All we have to do, we can apply Bernoulli equation between any point here of known characteristics. So if at a certain point 1, I know the value of P1 and V1, okay, then I can determine what will be the stagnation pressure. The stagnation pressure will be equal to the static pressure at point 1 plus the dynamic pressure at point 2. Okay. And we can say that for the stagnation point, all the kinetic energy will be transformed into pressure rise, into flow energy form. Okay. So the pressure energy is termed as flow energy. Okay. Now, how to measure stagnation pressure? We have some devices that are used specifically to measure the stagnation pressure. Okay, so what is the idea? The idea is that the stagnation pressure is equal to the static pressure plus rho v square over 2. Okay, let us consider the following device. And this device, the purpose of it will be to measure the velocity of a flow. So I can use the concept of stagnation pressure to measure the velocity of a flow. How to do this? If you look at the following figure, okay, I have a fluid flow. I have here at a certain section, I have a piezometer that will give me, this one will give me the static pressure. Because if I want to observe what is the pressure at this point, okay, I can look at the elevation, at this elevation of fluid above this point. So this device, when I read this height, this will allow me to measure what is called the static pressure at this point. Okay. Now, what I will do, I will force my fluid to stop isentropically through another tube. So I will force the velocity at this point here to be 0. And then the column height here will represent the stagnation pressure. So what I will measure here will be the stagnation pressure at this point, corresponding to B equals 0. Then I can deduce that the variation in elevation between these two columns is due to the rise in pressure, because all the kinetic energy was transformed into flow energy. So I can say that delta P reading, and delta P, you know that delta P is just measured by the height of this column. Because if I have the same fluid here, I can say that the pressure difference between this point and this one is equal to gamma of the fluid times this height here, times h. Okay, so this is why I can say that this device, by reading h, will allow me to calculate the velocity, because gamma f times h represent delta p between stagnation and static pressure, and delta p is just, when I take p to the other side, it's just rho v square over 2. So the value, the reading of h will allow me to calculate the value of my velocity. Okay, so gamma h is equal to rho v square over 2. This device is widely used in experimental fluid labs to calculate the velocity of it. So hope when you take the course of experimentation on fluids, you will use these devices. Okay. So now, let us remember what are the main conditions to apply Bernoulli equation. So the first condition to start with is to have a steady flow, because the equation that we derived together is applicable to steady flow, since we didn't consider the del by del t term. Okay. Now, another condition is to consider a frictionless flow. So we don't have friction, or we are away from any source of losses. Sometimes we can have friction, but it can be neglected. So then we can apply Bernoulli equation. A third condition, of course, we should not have shaft work. What do we mean by this? Let us say you are considering what is happening in a pump or what is happening in a turbine. Why you cannot use Bernoulli equation? Because in this case, you will have, let's say for a turbine, you have rotation. Okay, you have fans that are rotating, and these devices then will destroy the streamlines. So you don't have a smooth streamlines to apply along them Bernoulli equation. Okay. So when these devices exist, we should modify the energy equation, the Bernoulli. We should not use the Bernoulli equation as it is. We will use the energy equation, which will be derived in future chapters. Okay. Another condition is the incompressible flow condition. As I told you already, you should use the general Bernoulli equation if you have a compressible flow. So to use the common Bernoulli equation, you should have incompressible flow, rho should be constant. Now you know that for the issue of compressibility, some gases can be treated as incompressible. How to know in which case we can do the incompressible assumption? We can check the Mach number. If you remember, we defined the Mach number at the beginning of the course. We said that it's the velocity of the fluid, it's the velocity of light in a certain fluid, in the fluid of concern, over its velocity in sorry, one second. Okay, so we said that it's equal to the ratio of the velocity of sound in a fluid over, okay, the velocity of sound in air. Okay, so by this way you can get this number. It should be smaller than 0.3. In case it's larger than 0.3, you cannot consider that your flow is incompressible. Okay. Now, the fifth assumption is that you should not have heat transfer. And why? Because if you have heat transfer, then what can happen is that the density can change, because density is proportional to temperature. And therefore, in this case, I cannot use the common Bernoulli equation because rho will be variable. And finally, the final assumption is the flow along a streamline. So whenever I want to apply Bernoulli equation, points 1 and 2 should be along the same streamline. This means that, for example, if I consider flow over a certain object, okay, then I cannot, for example, take from point 1 to point 2 on another streamline. The 2 points should be along the same streamline. Okay. Let us do some typical examples of Bernoulli equation. Let us consider the following tank. Okay. And you want to, you opened your tank at level 2 and you want to calculate what is the discharge velocity at this level, Vt. Then here, what you can say is that I can consider the streamline, the following one, which is the path of water from point 1 to point 2. So first it's one streamline because I have line of flows. So I have here several streamlines, okay, a series of streamlines. I can take the one that is far from walls. So I will take the streamline passing by the center. So I will be considering the following line. Okay. Now I have that by applying Bernoulli equation between 1 and 2, I have P1 over rho G plus V1 square over 2G plus Z1 equals to P2 over rho G plus V2 square over 2G plus Z. Okay. Now, first, I have at this level, let's say it's open to the atmosphere. P1 is open to the atmosphere. So P2, P1 is P atmospheric. Or if I'm dealing with gauge pressure, if I'm considering gauge pressure, P1 is 0. And also at 2, my section is discharging towards the atmosphere. So also the pressure at 2 is equal to P atmospheric. Therefore, P1 and P2 terms will cancel out, and both are 0 gauge pressure. Okay, now I am done with the pressure terms. Now concerning velocity, at the discharge section, I want to get what is V2. This is my unknown. And at section 1, I have a velocity, but this velocity can be neglected. You know why? Because you can write that in steady case, V1 times A1, which is the velocity the water will move down, will be equal to, this is the volumetric flow rate Q, okay, will be equal to V2A2 because of continuity, as we have seen before for the examples of pipes. Now, since area 1 is much larger than area 2, okay, so since A1 is much larger than A2, and A1 V1 is equal to V2 A2, so we can say that V1 is much smaller compared to V2. So we can neglect this term V1 square over 2G compared to V2 square over 2G. Okay. Now, then what will happen is that this term will cancel out. And now we have Z1 represent, which for Z1 and C2, we need a certain reference. We can consider the reference of Z at level 2. So Z2 is 0. Okay. So then we can now say that the velocity V2 can be obtained from the following equation. Z1 equals to V2 square over 2G. And this is very physical because larger is the height of water in the tank, larger will be the discharge velocity. Okay. In this way, the potential energy will be transformed into kinetic energy as you move from 1 to point 2. Now, another example, if I considering the following jet of water, okay, and what I am doing is that I'm putting my thumb at section 1, and I want to determine, okay, if I let's say if I close my thumb, what will, or if I put my thumb here at just at point 1 and I open it so water can flow out, okay, what will be, for example, the maximum height that can be reached here by water, for example. Okay, so what we can do then is that we can apply a Bernoulli equation between section 1 and the maximum height reached by water Z2. So I am interested into calculating what is the maximum height reached by water. So I will consider a certain streamline of the fluid. This is point 2 and this is point 1. Now, if I write the equations, I have the pressure at 1 over rho g plus V1 square over 2g plus Z1, okay, equals to the at point 2, the jet is exposed to the atmospherical pressure. So P2 can be replaced by P atmosphere. And now, since I reached the maximum height, I reached the maximum height at Z2, okay, then V will be 0. V as Z2 will be 0. So I will just have plus Z2, okay. And I still here now want to get what is the following term, okay. If you look at your system, what you did is that before you opened your sump, before just you opened your sump so that water will flow out, okay. If you know what was the pressure at this level, okay, then you can write that what is happening is you have the velocity at point 1 just before opening is 0. And what you will do here, you will consider that you know the pressure just before opening your sump. So when your sump was completely closing the jet, you know the characteristic pressure P1, and the velocity was equal to 0 because this was closed. Okay. Now, when you opened the path for water to move out, then if water will flow upward. So we will consider the point 1 just before, if you want, just before letting the flow pass through your system. Okay. So you can say, or also the analysis you can do is the following. If I consider P1, because look, the streamline will be directed from the tube towards, and it's getting outward to go up, okay? If you take a section that is here, at this level, so you will not take point 1 just here near your sump, as we said, because we consider always points far from walls or far from boundaries, okay. So I will take point 1 just here before the opening, the small opening that I made, okay. And since I'm taking point 1 far away from this point here, I can say that the velocity at this level can be neglected compared to the velocity here, because I just opened my sump for a very small area. So also here you can consider the area of the jet is much smaller than area at section 1 here. So you can neglect this velocity. And you can understand this by another way. You can say, what is the pressure within the tube here? Okay, so when my sump was just closed nearly, I have a certain high pressure. So when I open a little bit, this high pressure will allow the fluid to exit, okay? And the velocity here is negligible compared to the velocity at this level, so I can neglect it. And then I can deduce that the pressure inside my tube over rho g is equal to P atmospheric over rho g plus Z2. If I do the analysis of this expression, I can see that, of course, higher the pressure in my piping system, higher the elevation I can reach, of course, because the flow energy, which is energy that is accumulated in the fluid due to pressure, will be transformed into potential energy. So when you were closing the sump completely, the energy is stored into form of flow energy or pressure. Okay, pressure flow energy. When you remove your sump, this type of energy can be converted. First, it was converted here to kinetic energy, and as it go upwards, it will be transformed to potential energy. Okay. Any question on this? Okay, sorry for taking more time. In case you have any questions for the exam, let me know.
دكتور
Yes,
معي سؤال للإكزام.
yes. So just let me stop recording.